Assalamu alaikum and good morning. So today I'm going to do correction. It's like post-mortem on the exercise 22.1, and based on the questions that you guys have voted, I've only received 21 responses so far. So that means 8 of you have not filled in the form. So I'm just going to use whatever data that I have right now, okay? So the first question that I'm going to look at is question 1, okay? So which of the following species will deflect it to the greatest extent? So biggest deflection usually happens to the lightest species, okay? It has to be charged. So C is not an option because C is neutral. So if it's a neutral species, it will not get deflected. It will just continue to travel in a straight line. Now, not only that we are looking at the mass, but we need to look at the charge as well. Okay, so that's why I always warn you to be careful with using the term mass. It's actually mass to charge ratio, okay, M/E. So if you do your calculation, taking into account of the sodium with a charge of +2, if you take 35 divide by the charge, which is 2, you'll get 17.5, and D is the species that will be deflected the most because it is the lightest mass to charge ratio. Okay. Next is question 7. Okay, so question 7 is a little bit tricky because you don't have numbers. However, I've used this technique in one of the lessons that we did for topic 22. Basically, you just take the height of your peak, and that will be, say, 1, okay? And then you just times by how many times of that 1 unit makes up this height, okay? You don't need to use a ruler. I just used approximation, estimation of the height of these two peaks. I assume that these two peaks are I assume that the two peaks are similar height, and I make them as my 1, okay? And then it turns out that this height for the mass to charge ratio of 28 is 10 times of the smaller ones. So my ratio is 10 is to 1 and is to 1. So that means the ratio for my mass to charge of 28 is 10, and the ratio of my mass to charge of 29 is 1, and the ratio of my mass to charge of 30 is also 1. Okay, so if I make them as a fraction, it turns out that my relative abundance for my isotope 28 is 10/12, isotope 29 is 1/12, isotope 30 is 1/12. Okay, how do I know that? I take the total of the numbers in my ratio, 10 plus 1 plus 1, the total is 12. Okay, so if you were to do the calculations, like how you would normally do to find out the relative atomic mass, which is you take the relative abundance times by the isotopic mass for one isotope plus the relative abundance times by the isotopic mass of the second isotope plus the relative abundance times by the isotopic mass of the third isotope. Okay, so you should get it as 28.3 or something close to that number. Okay, right. So the next ones we're going to look at is 9, 10, and 11. Okay, right. So for question 9, which alcohol is not likely to have a fragment at mass to charge ratio of 43 in its mass spectrum? Okay. Okay, so for the signal or the peak at 43 is usually typical of your C3H7 plus fragment, okay? The best way to do this is to draw out these structures and see if there is a fragment that can produce a signal at 43. Fragmentation usually occurs when you break any carbon-carbon bond, okay? So here is, I've drawn your molecule A, where if I have fragmentation here, okay, then this part will give a peak at 43, okay? It has to be a positively charged species. For my molecule B, if I break it here, if I fragment my molecule there, I would get a peak at 43 caused by this C3H7 plus species. As for C, again, I draw out, I also can break my molecule here, and then this part of my fragment with a positive charge will give a signal or a peak at 43. Whereas for D, okay, if I break my bond here, I will get either a peak of at 15, or the other side is, I haven't calculated this. So 15 plus 12 plus 1 plus 16 plus 1 plus 12 plus 2. So that is 59, okay? This side 15, on the right side is 59, okay? What if I break it here? That is the CH3, CH2. So that is, this will cause a peak at 29, okay? What about the other side? 15 plus 12 plus 1 plus 17. This will be 45, okay? So there is no way for you to get a fragment of 43 in molecule D. Remember, fragmentation or the breaking of the bond usually occurs on the carbon-carbon bond, okay? So you cannot do this. That means you are breaking a C single bond O, okay? Right, so the answer is D. If you want to copy this down or draw it out, please pause the video. Next, I'm going to move on to question 10. Same thing, which of the compounds below is not likely to have a fragment at mass to charge ratio of 43? Again, 43 is the typical mass to charge ratio for the fragment C3H7 plus or anything that's related to it, okay? So C and D, you can see that's your C3H7 fragment. D is that, okay, that is possible, C single bond O. You have a C3H7 plus as well. B is when you break or when you've broken down your molecule at the C single bond O, okay? So this side of the molecule will give you a peak or signal at 43, okay? Whereas A, if you break it here, that's 15, and the other side is, I should have done this earlier. The other side would be 12 plus 2, plus 12 plus 16. Sorry, 12 plus 2 plus 12 plus 16 times 2 plus 1. 59, okay? So if I break it here, then I've got either 15 or 59. And then if I break it here, I would get a 29 on this side. As for my COOH, that's 45, okay? So it's not 43. And if I break this, I believe that is, that's 59, I think. 12 times 3 plus 5 plus 16, 57. 12 times 3 plus 5 plus 16, yeah. If I break it here, this side will be 57. So there will be no possible fragment in molecule A that can arise or give a peak or signal at 43? Okay, for question 11, assuming that chlorine has only 2 isotopes and hydrogen and carbon as 1. Now, the chlorine, the isotopes that we know are chlorine 35 and chlorine 37, okay? How many molecular ion peaks will be shown in the mass spectrum of C4H6Cl4? There are 4 chlorine atoms in this formula, in this molecule. And there are 2 types or 2 isotopes of chlorine. So how many molecular ion peaks? Molecular ion peaks are the signals produced by the molecules that have not been fragmented. So you don't break any bond. You have the molecule as a whole, but with a positive charge. Now, why is the answer A? Because you can have a combination of all 4 chlorines in this formula. Since it's C4H6Cl4, I don't care where the chlorine is seated actually. The most important thing is all the chlorines, all the 4 chlorines are made up of chlorine 35, in which case the peak or the signal will be at 140. Okay, the second possible combination is all the chlorine, all 4 chlorines are made up of chlorine 37, in which case I have a signal or a peak at 148. The third one is when I have one of the 4 chlorine is made up of chlorine 35 and the other 3 is made up of chlorine 37. Okay, the fourth one, 2 chlorine 35 and then 2 chlorine 37. Okay, and last one is 3 chlorine 35 and 1 chlorine 37. So those are the combination, and the signals you would see if you count the MR for each of these molecules. It's 140, 142, 144, 146, and 148. Do you notice that the difference between these numbers are units of 2? Okay, so you add on 2 units from the first number to the next one. So that's why the answer is 5, because of the possible combination of your chlorine isotopes. Which pair compounds would you expect to both have a singly charged peak at 29? So if 43 is typical of a C3H7, then 29 would be a typical of C2H5 or anything that is closely related to it. Okay, so the answer is propan-1-ol. Propan-1-ol is an alcohol with the hydroxy group on the first carbon. So if I break my alcohol here, you can see that I have a CH3CH2 fragment that can produce a signal at 29. Whereas propanol is an aldehyde with 3 carbons, same thing. If I break the CC bond here, this fragment is a CH3CH2 plus fragment, which will result in the peak at 29. Okay, so propan-1-ol and propanol is possible. Propanone, why is propanone not possible? Okay, if I break it here, I will have 15 on this side, and then on the other side, another possible fragment would be, I believe that's 43. Okay, same thing. If I were to break it here, I can only have 15 and 43. So propanone can never produce a fragment that give a result in a peak at 29. Okay, what about propan-2-ol? So propan-2-ol is your alcohol with your hydroxy group on the second carbon. Same thing. If I break it here, I would have 15 and the other side would be 45. How do I know that? You just count the MR as you would normally. If I break it here, I would have 45, a fragment for signal at 45 and another fragment for signal at 15. Again, it is impossible to have a fragment that would result in the signal or peak at mass to charge ratio of 29. Next question would be question 15, okay? Right, if I don't look at my options yet, I just look at this spectrum. I will only focus on above the 1500 mark, okay? So first thing is that this peak is usually, it looks like a typical peak for C double bond O, okay? And then the other noticeable thing is that there is no broad peak for OH, whether it's OH of carboxylic acid or whether it's OH of high alcohol, okay, hydroxyl. This peak does not represent the peak of OH because usually OH is broad or wide. As you can, this is usually the typical peak of OH, okay, and that's missing in this spectrum. So this would have been caused by what are the numbers that you have here? CH, okay, but there are two types of CH. CH alkane is the one that is at the lower site, which is below 3000, okay, whereas sorry, yeah, it should be between 2800 to 2900, whereas the CH of aldehyde is even lower, okay. You should see a peak at 2800 to 2900, and then also between 2700, like that, okay. So that's missing. So it looks like the CH is the one for the region above 2900. So that means it probably belongs to alkane, okay? Then only I will look at the possible the given options, okay? So as I said, no OH peak, so it cannot be your alcohols A and B. So now you're left with propanol and propanone. Both of them contains the C double bond O. Okay, the only thing that's different between these two would be the CH. Okay, the CH of aldehyde will produce a much lower peak or a much lower signal. Okay, so that means it cannot be aldehyde. You are left with propanone. Okay, the CH is of alkane. And how can you call that alkane? Because it's CH3, your alkyl group. All right. Next question is question 19. Data from the mass spectrum of a sample of pure iron. So that means you only have iron. Automatically, your Si, what's that? Strontium and silicon will be eliminated. Okay, you should not have a signal that is produced by strontium or silicon, only iron. Okay, so you're left with 56 Fe2 plus and 28 Fe plus. Iron has a mass of 56. Well, actually, if you look at the AR, it's 55.8. Okay. It cannot have an isotope that has a mass of 28. Okay. Another reason why this is impossible is because, where is iron in my periodic table? Okay, so iron, usually isotopes, the mass would not be very, very far. Like if iron has a mass of 56, the isotope would either be 57, 58, or 54, 55, something like that. Okay, but it wouldn't be as far as 28. Okay, so iron 28, it doesn't exist. So you are only left with option C. Okay, again, how can 56 Fe2 plus produce a signal at 28? It's because you take the mass to charge ratio. Mass is 56, charge is 2. Okay. Next question is question 21. For this question, again, the spectrum is given to you. So I would start with analyzing the spectrum quickly. Okay, so again, there is a peak at, I don't know, 1700. Okay, and that is a typical peak for C double bond O. There is a peak for OH, but I still don't know if it belongs to alcohol or carboxylic acid, but it's towards the higher side, close to 3,500. So it's between 3,300 and 3,500. Okay. And then there's another peak that looks like CH. Okay. But that's not usually a significant peak. Okay. So what I can conclude from the spectrum is that it contains C double bond O, it contains OH. It's just that I don't know which OH yet. Okay. So for A, there is a C double bond O and there's a OH. So I wouldn't eliminate it first. B, there's a C double bond O and there's a OH for alcohol. C, there is no C double bond O, so C can be eliminated. As for D, there is no OH bond, so D can be eliminated as well. So we are torn between alcohol and carboxylic acid here, so you have to look at the values. Carboxylic acid values are a bit lower, between 2,500 to 3,000, whereas the hydroxyl for alcohol is between 3,200 and 3,600. So you can see here that this peak is a bit towards the higher side. Okay, so that is suspected to be hydroxyl between 3,200 and 3,600. So the answer is B. Okay, so the OH belongs to hydroxyl. I remember a few students asking me what is hydroxyl. Basically, hydroxyl is an alcohol. Carboxyl is a carboxylic acid. Okay. Next is 22, same thing. Again, I will only analyze the region above the 1500. There is a typical peak of C double bond O here. My OH is definitely missing. There are some peaks here, and that is not OH peak because OH is usually wide or broad. That looks like a CH peak. Okay, so what can I conclude from this spectrum is that my molecule doesn't have an OH bond, but it has the C double bond O. Okay, so butanoic acid contains an OH bond, eliminated. Butanal contains a C double bond O, possible. Butan 1-ol contains OH bond, which is eliminated because the spectrum doesn't contain a signal for OH bond. 1-bromobutane, it doesn't have a C double bond O. Okay, so that means by elimination and also because it fits with the data, the answer is B. This spectrum belongs to butanal because it contains a C double bond O and butanal doesn't contain an OH bond. All right. Next is 23. Which of the following inferred spectra could show a carboxylic acid? So the significant peaks of carboxylic acid is CO and the OH bond. Okay, so you can see here that is a typical CO signal, and that looks like a typical OH signal, but we'll have a look at the other spectrum first, okay? Other spectra. For option B, it's missing the C double bond O peak at 1700, okay? C, that actually I'm not sure if that is a C double bond O peak because it's too narrow, okay? But one thing for sure is the OH wide OH, the broad OH signal is missing, okay, as well as D. So don't be tempted to think that this belongs to the OH bond, okay, because usually OH is smoother, okay, and it's wider, right? So the answer, the best answer here would be A, because it's got both the peak for C double bond O and the peak for OH as well. Last question is question 25. So I'm going to use the information first. What the mass spectrometry can tell me is that the molecular ion peak is at 128. So that means the MR of my molecule is 128. Okay, there's a fragment ion peak at 15. So that looks like it's a CH3 plus signal. Infrared spectroscopy tells me that there is a sharp peak at 1720. So that is possible of a C double bond O. There is no broad peak around 3200. So that means there's no OH bond in my molecule. Okay, so by elimination, I do not have an OH bond. B is eliminated. I also do not have OH bond for carboxylic acid. Okay, so either it's an alcohol or carboxylic acid, both are eliminated automatically. So that gives me option A and C. Now, another hint that I can use is the MR, right? If you check, I don't know if I did it correctly, but the MR for molecule C is actually 129. Okay, can you please double check that for me? And based on the data I have here, the MR for this molecule, this unknown molecule, is 128. Okay, and there is a fragment of CH3. Well, there can be a few fragments of CH3 here. Okay, so the answer is A. C is not the answer because the MR does not add up to 128, but I could be wrong. Can you please double check it for me? Okay, and that's it. I hope I have answered everything, all the questions, most of the questions that you wanted to ask me. If you still have doubts on a particular question and you want me to explain it to you, can you please contact me privately? I will explain it to you on WhatsApp. Okay, Assalamu alaikum and thank you everyone.